Hello. In my last lecture, I discussed about the behavior of a solute when distributed between two immiscible liquids in contact with each other. The ratio of concentration of the solute in the two liquids is found to be constant. But there are conditions of validity which are summarized in Nernst distribution law. We also looked at these special cases where the solute gets associated or dissociated in one of the solvents. We also try to derive the Nernst distribution law from thermodynamic considerations. In today's lecture, I'll talk to you about the Nernst distribution law, the special case of it in which there is complex formation. Then we discuss about the various applications of Nernst distribution law, which include study of association of a solute in one of the solvents, study of dissociation of a solute in one of the solvents, distribution indicators, study of complex ions, and finally, a very important application of solvent extraction. Let's start with case 3. We have seen, if you recall, case 1 and 2 in the earlier episode. In this, we deal with a situation where solute enters into chemical combination with one of the solvents. So, when the solute enters into chemical combination with one of the solvents, the system is found to obey Nernst distribution law. The ratio of concentrations of the solute in the two phases is found to be constant as expected. However, detailed analysis shows us that numerical value of the constant is found to be different. Let C1 be the concentration of the solute X in liquid phase 1, in which it remains unchanged, and C2 be its total concentration in phase 2, in which the solute enters into chemical combination with the solvent molecules, forming complex molecules. The resulting equilibrium can be represented as X plus Ns in equilibrium with XNS, where XNS stands for the complex molecule between the solute and the solvent molecules. N is the number of solvent molecules associated with one molecule of X. This can be clearly seen in this figure. We have two phases in equilibrium in contact with each other. The solute X gets distributed between the two phases, establishing the equilibrium. When the established equilibrium is there, we can clearly see that in the second phase, molecule of X forms a complex molecule with the solvent molecules. The concentrations in the two phases, as we can see, is C1 and C2, and if alpha is the fraction of the solute that enters into chemical combination with the liquid in phase 2, then the concentration of the various molecular species in equilibrium can be given by concentration of uncombined solute molecules is equal to C2 into 1 minus alpha, whereas concentration of the complex molecules formed will be C2 alpha. We can now apply the law of chemical equilibrium to the equilibrium existing in liquid phase 2. We get K, the distribution coefficient, equal to C2 alpha divided by C2 into 1 minus alpha, concentration of the solvent raised to N. But we know that the solvent is in large excess. Therefore, we can take the concentration of the solvent to be a constant. Hence, we can write C2 alpha upon C2 into 1 minus alpha equal to constant. Taking this as equation 1, The distribution law is valid only for the concentration of similar molecular species. We have been repeating this. That is, if we take the concentration of single molecules of X, then we can apply distribution law. Hence, C1 upon C2 into 1 minus alpha is equal to constant. This is equation 2. Now, dividing equation 2 by equation 1, we get C1 upon C2 alpha is equal to constant. We know that alpha, the fraction of the solute that combines with the same solvent, is also a constant at a given temperature. Therefore, equation 3 may be written as C1 upon C2 equal to constant. This is the original equation for Nernst distribution law. So, when there is complex formation with the solvent molecules, the ratio remains constant, but combination with the solvent molecules does change the numerical value of the partition coefficient, because the constant that we have written C2 includes alpha. Let us look at the applications of Nernst distribution law. We have seen different cases, and these cases can be suitably applied to find out the information that we want. Study of association of a solute in one of the solvents. If a solute associates in one of the solvents in which its concentration is C2, but not in the other solvent in which its concentration is C1, then we can write C1 upon nth root of C2 is equal to Kd. Kd is the partition coefficient. N being the number of simple molecules which combine to form one associated molecule, like a dimer, a trimer, etc. It has been possible to show by experiment on distribution of acetic acid and benzoic acid between water and benzene that these substances exist in benzene as double molecules or dimers, as shown in the figure here, where the value of N is 2. Let us now look at the study of dissociation of a solute. As has been shown earlier, if the solute undergoes dissociation in one of the solvents in which its concentration is C2, but not in the other solvent in which its concentration is C1, then we can write C1 upon C2 into 1 minus alpha is equal to Kd. But if the degree of dissociation alpha of a solute is known at one of the concentrations, its value at any other concentration can be obtained, since Kd is constant. So, this is the application that we can think of Nernst distribution law. The third application is distribution indicators. It is a common experience that iodine distributes itself considerably more in carbon disulfide than in water when both the solvents are in contact with each other. Therefore, an extremely dilute solution of iodine in water can be successfully titrated by adding a drop of carbon disulfide. Since the volume of carbon disulfide is low, the iodine concentration makes it to get the color. We can see it clearly. So, titration becomes easier because we can now recognize the color in that small drop of carbon disulfide. Study of complex ion. It is a very interesting application. Nernst distribution law has been successfully applied in determining the formula of the complex ions formed between bromine and bromide ion, as well as between iodine and iodide ion. The best example that we can think of is the study of complex formed between iodine with potassium iodide. On stirring a solution of iodine in carbon disulfide with water, the iodine distributes itself between the two solvents in accordance with the distribution law. Knowing the concentration of iodine in the two layers, we can calculate the partition coefficient Kd. Once we have that value of Kd, it can be used whenever we have such a situation or such an equilibrium established. We can see here we have two layers, aqueous layer and carbon disulfide layer. In carbon disulfide layer, iodine is present in large concentration. When we shake the two layers, iodine gets distributed between the two layers. If potassium iodide were not there, it would have reached the equilibrium under normal circumstances to give the value of Kd. But since Ki is present, iodine will tend to form a complex, say Ki3. If a solution of iodine in carbon disulfide containing X moles of iodine per liter is shaken with an aqueous solution of potassium iodide containing A moles of potassium iodide per liter, iodine tends to form complex with the Ki in aqueous medium. The total concentration of iodine in the aqueous layer will therefore be much higher than the simple water if we take, because of the formation of the complex ion or complex rather Ki3. Let this concentration be moles per liter. So, because of this, the concentration of iodine in carbon disulfide layer will fall from X to X minus B moles per liter. According to Nernst distribution law, the concentration of free iodine as I2 in the aqueous solution is given by Kd into X minus B. We can take it as D moles per liter. Suppose the complex ion formed is I3 minus. Then the following equilibrium will exist in the aqueous solution: I minus plus I2 in equilibrium with I3 minus. Evidently, B minus D moles of iodine must have combined with B minus D moles of iodide ions to give B minus D moles of the complex ion I3 minus. The equilibrium constant will be then given by K equal to concentration of I3 minus divided by concentration of I2 into concentration of I minus. The concentration of the various species in the aqueous layer will be I3 minus is equal to B minus D moles per dm cube. Concentration of I2 is equal to D moles per dm cube, and concentration of I minus is equal to A minus B minus D moles per dm cube. Now, let us find out how valid is this discussion that we have made about the complex ions. Here is a table which gives the results of determinations carried out at 30 degrees centigrade for the above reaction. The values of A, B and D as found out from experiment are given here. Using these values, K is calculated. The partition coefficient K is calculated. You can see here the values are 19.72, 20.04 and 20.40. The fact that K is reasonably constant in spite of variation in the values of A and B shows that the formula of the complex ion is I3 minus. Otherwise, we would not have got constancy in the values of K. It is now time for us to discuss the most important application of Nernst distribution law, the solvent extraction. So, as I told you, it is the most important application not only in laboratory but also in industries, the process of extraction. In the laboratory, we frequently use this method for the removal of a dissolved organic substance from aqueous solution with solvents such as benzene, ether, chloroform, carbon tetrachloride, etc. The advantage is taken of the fact that the partition coefficient of most of the organic compounds is very largely in favor of the organic solvents, and we use in the laboratory a separating funnel as shown here. We have the stopper and the stopcock here, and the shape of which we can clearly see, which helps us to clearly separate the two layers. The two layers that are there, the denser layer will be settling at the bottom, the less dense layer will be over it, floating over it. We have to mix the two layers thoroughly by inverting the separating funnel. During that time, we have to hold the stopper tight and keep the stopcock closed and occasionally release it in order to release the pressure that may build up inside. And then fix the separating funnel vertically on the stand here and allow it to attain equilibrium. The two layers will separate, and once equilibrium is attained, we can open the stopcock and take out the lower layer, and the two layers after separation can be subjected to analysis. The same principle applies in the desilverization of lead by Parkes process, which you have seen earlier. The argentiferous lead, if you recall, is melted and heated to 800 degrees centigrade. Molten zinc is then added to it. Molten lead and molten zinc behave as if they are two immiscible liquids in contact with each other. Silver behaves like a solute which is distributed between the two layers now, but it is more soluble in zinc than in lead, the partition coefficient being of the order of 300 at 800 degrees centigrade. So, what we do? We take molten argentiferous lead, add calculated amount of molten zinc to it, and agitate the two thoroughly in order to allow silver to pass from the molten argentiferous lead to molten zinc till the equilibrium is achieved, and then separate it. This is one of the methods whereby silver can be extracted, which is of very poor quality in that. Silver is very low in concentration, but you can concentrate it, and once you have increased the concentration of silver in that, you can then subject it to further purification. Now, it is possible for us to derive a formula which helps us to calculate and improve the efficiency of extraction. It is a general formula which enables us this. Let us take V ml of a solution containing W gram of the solute, and we extract it with small aliquots of small v ml of another solvent which is immiscible with the original solvent. While doing so, let W1 be the mass of the solute that remains unextracted at the end of the first operation. What we are doing? We are taking a solution containing W grams of the solute. To that we are adding the extraction solvent in small aliquot of small v ml, and then shake it thoroughly and allow it to stand. While doing so, W1 is the mass of the solute that remains unextracted out of the total of capital W grams. This can be shown by calculating the Kd, which is given by small w1 by V divided by capital W minus W1 upon small v. Or we can rewrite this equation: the amount of solute remaining unextracted after the first operation, that is small w1, is equal to capital W into Kd into V divided by Kd into V plus small v. We can repeat the process in that let W2 grams of the solute remains unextracted after the second operation, and similar formula we can calculate. W2 is equal to W1 into Kd into V divided by Kd into V plus small v. We can introduce the result of the first operation so that we get W2 is equal to capital W into Kd into V divided by Kd into V plus small v raised to 2. We can extend it to third, fourth, fifth and to the nth operation and write the formula that we expect after the nth operation for the amount of solute remaining unextracted. Wn is equal to capital W within brackets Kd into V divided by Kdv plus V raised to n. So, it is evident that in order to make Wn as small as possible, that means to increase the efficiency of extraction for a given value of Kd, n should be as large as possible. But we know that n into small v is equal to the total volume of the extracting liquid available to us, and it is constant. Therefore, it is better to keep n as large as possible and v small rather than the reverse. In other words, to increase the efficiency of extraction, we must divide the available extraction liquid into small aliquots and carry out the extraction several times in order to get the maximum extraction efficiency. For the same reason, if you recall, in the lab, in the washing of precipitates, it is more effective to use a small quantity of water at a time and to repeat the process a number of times. You must have surely done it in your gravimetric analysis. Let me summarize what we have discussed today. We continued our discussion on Nernst distribution law, especially after completing case 1 and case 2 in the earlier episode. We saw the special case 3 where there is complex formation, and then the applications of Nernst distribution law is discussed, in which we saw study of association of a solute, study of dissociation of a solute, distribution indicators, study of complex ions, and finally solvent extraction. With this lecture, we complete our entire discussion on phase equilibrium, right from the definition of the terms involved till the final application, which includes one component system, two component systems of various types. Solvent extraction is an offshoot of phase equilibrium, which we saw in the last lecture.